How do you teach a machine to understand a sentence like, "Someone in this room is a doctor"? It seems simple, but a question like that actually breaks basic logic. Today, we're going to dive into the powerful upgrade that makes it all possible, predicate logic.
Okay, let's kick things off with something really simple. The statement, 20 is smaller than 10. We can all agree, that's just flat out false, right? In the world of basic logic, what's called propositional logic, everything is black and white. A statement is either completely true or completely false. There's no in-between.
But what if we throw a little wrench in the works? What happens if we just swap out that number 20 for a variable? Say x. So now our statement is x is smaller than 10. And believe it or not, this tiny change pretty much breaks everything.
All of a sudden, we're stuck. We can't answer the question anymore. Is it true? Is it false? Well, it totally depends on what x is, right? If x is 5, sure, it's true. But if x is 15, then it's false. Without knowing what our variable is, our simple logic system just grinds to a halt.
And this, right here, is where our basic system, propositional logic, just hits a brick wall. See, it's designed for a world where everything is certain. But the moment you introduce a variable, an unknown, the whole thing just starts to fall apart. Let's take a look at why.
Yeah, you can think of propositional logic as a really picky vending machine. If you give it a complete statement like 5 is greater than 2, it's happy. It spits out true. But if you try to give it something like x is greater than y, the machine just jams. It has no idea what to do with variables or the relationships between them. It's just way too rigid for most of the problems in the real world.
So to fix this, we've got to level up. We need a logic system that's way more powerful and a lot more flexible. And that system is called predicate logic.
Now, it's important to know, this isn't a replacement. Think of it more like an expansion pack. It takes all the good stuff from propositional logic, but then adds this absolutely crucial new feature, the ability to handle variables and talk about how they relate to each other. It lets us get so much more nuanced.
So, how in the world does it do this? What's the secret sauce? Well, it introduces two incredibly powerful new tools. And these tools are called quantifiers. Okay, let's meet our two new players. On the left, we've got the universal quantifier. It means for all. We're going to call this one the perfectionist. And on the right, there's the existential quantifier, which means there exists. We'll call this one the optimist. And trust me, these nicknames are going to make a ton of sense once you see them in action. But wait, before we can let these guys loose, there is one super important rule we have to follow. We have to define the universe of possible values for x. This set of allowed values is called the domain. It's basically us setting the boundaries for our test, saying, hey, you're only allowed to play with the numbers in this sandbox. All right, time to put our first tool to work. Let's start with the universal quantifier. Remember, this is our perfectionist, and it lives by a very strict all or nothing rule. Now, the notation might look a little weird, but don't worry, this upside-down A just means for all. So when you see this, it's just asking a question. For all the possible values of x that we've allowed, is our statement true? So for us, the question is x is smaller than 10 true for every single value we're about to test? Okay, let's set up a simple domain for our test. The universe for our variable x is going to contain just 4 numbers, 1, 3, 5, and 7. So let's run the check. Is 1 less than 10? Yep. Is 3 less than 10? Check. 5? You bet. 7? Absolutely. Since every single value in our domain made the statement true, our little perfectionist is satisfied. The final verdict for the whole thing is true. But what happens if we mess with it a little bit? Let's just change one of those numbers. We'll swap out that 7 for a 70. So our new domain is 1, 3, 5, and 70. All right, let's run the test again. 1 passes, 3 passes, 5 passes, but 70? No, 70 is definitely not less than 10. And for our perfectionist quantifier, that one single failure is a catastrophe. The entire statement becomes false. It's because this is basically a chain of ands. It needs the first one and the second one and the third one to be true. The second one part is false, the whole chain just breaks. Okay, so that was the strict one. Now let's check out our second tool, the one with a much more relaxed attitude. This is the existential quantifier, our optimist, and it lives by the just one is enough rule. So the notation for this one is this backwards E, and it asks a completely different question.
It asks, does there exist at least one value of x in our domain that makes the statement true? See, we're not looking for perfection anymore, we're just searching for a single success story.
For this test, let's use a new domain, 5, 15, 25, and 35. Now you can probably already see that most of these numbers are definitely not going to be less than 10.
So, let's start checking. First up, the number 5. Is 5 less than 10? Yes, it is, and we can stop right there. That's it, we're done. Our little optimist found the one success it was looking for, so the entire statement is declared true. It's like a chain of ors, you know? As long as you find a single true in the bunch, the whole thing becomes true.
So let's wrap this all up. We started with propositional logic, which was great for absolutes, but couldn't handle variables. So we leveled up to predicate logic to solve that problem. And we learned about its two secret weapons, the perfectionist universal quantifier that needs all values to be true, and the optimist existential quantifier that only needs one value to be true.
And why does any of this really matter? Well, because this is how we teach machines to reason about the world in a way that's much more sophisticated. When we give them a formal language to understand the huge difference between a concept like all and a concept like sum, we're moving them away from just being calculators. We're actually taking the first critical steps toward genuine understanding, the very foundation of artificial intelligence.